Hello, and welcome back to Castle Microwave's How to Build a series. In this episode, we will be constructing a reflector antenna and analysing its far-field performance. If you haven't watched episode 1, I highly recommend doing so, as we will be using the horn antenna we built there in this implementation. Reflector antennas use a curved surface with cross-sectional shape of a parabola to direct radio waves. This allows them to have high directivity. Because of this, they are suitable for high-gain point-to-point communications, SATCOM, and spacecraft communications. The exercise will cover the construction of the reflector and calculate the far field of the complete system using the hybrid solver task. Let's proceed by opening CST Studio Suite. If we go to New Template, select Microwaves and RF Optical and Antennas, and then Reflector, then we reach the recommended solvers section for this workflow. The integral equation solver is of special interest for electrically large models. The discretization of the calculation area is reduced to the object's boundaries, and thus leads to a linear equation system with less unknowns than volume methods. For calculation efficiency, the equation system is solved by the multi-level fast multiple method for electrically large models. For the direct solver, the system matrix is dense. The integral equation solver is available for plane wave excitation, discrete phase ports, discrete edge ports, waveguide ports, far field source excitation, and RSD current sources, as well as simultaneous excitations of them. The solver can be used to perform a characteristic mode analysis. Electric and open boundaries are supported. E-field, H-field, and far field monitors and surface current monitors can be set in the integral equation solver. Since the integral equation solver is based on non-local operators, every element couples to all other elements. This leads to a linear equation system with a dense system matrix. There are different approaches to solve the resulting memory and time problems. The equation system can be solved directly by the direct solver for small and medium problems. The dense matrix can be approximated by ACA for electrically small or medium problems. Both solvers are available in special accuracy integral equation solver parameters. Last but not least, the multi-level fast multiple method can be used to approximate the matrix vector multiplication of the system matrix and logically uses it within an iterative equation solver to obtain the solution. In order to obtain the approximation of the matrix vector multiplication, neighbour elements are united in boxes. The coupling of all elements of one box to another is approximated by the coupling between the boxes themselves. Using a recursive and hierarchical scheme by means of unification of smaller boxes to larger boxes leads to the multi-level fast multiple method. This shape forms the reflective surface in the antenna that enables waves reflected by the surface to retain their phase relationship, thereby enabling the maximum gain to be obtained. Now select Next. For dimensions, we're going to use centimeters, gigahertz, and nanoseconds. It's okay to leave the rest of these as they are, as they're not going to be necessary for our design here. For our frequency, let's set this between 9 and 10 gigahertz, and we'll monitor the far field and E field. We're only looking at the 10 gigahertz frequency. We'll give this a suitable name. Reflector will do just fine. Click Finish. Before we go any further, let's save our file in a suitable place. Let's call it Reflector. Before we go any further, let's declare some variables. So we'll go for the dish diameter, dish D, and we'll put that to 50. And for adjusting the focus, we'll put dish F, and we'll set that to 0.45. Now if we go to macros, and construct, and parts, there's a macro here available to generate a reflector dish. We set the diameter then to dish D, and the focal length of the reflector to dish F, press OK. It then constructs a dish for us to the dimensions we specified, and the pick point provided is the focal point of the dish. If we now go to File, New and Recent, Circuits and Systems, select Assembly, and then save this as SAM horn reflector in an appropriate location. Then let's change our units to centimeters. Define a parameter as dish focus, and we'll set that to 22.5. Hit save quickly, and then if we import 3D blocks, we can go and import the horn and the reflector we have made previously. So there's the horn. Do the same again. There's the reflector. Now we need to place the horn in the correct position relative to the reflector, as the horn should illuminate the reflector, and its aperture, which is the phase center position, should be placed in the reflector focus. So if we select our horn block and select absolute transform, and now let's define our translation as 180 degrees as our rotation, so it's facing the right way. And now it's facing the right way, let's set our Z coordinate as our dish focus, and then +7 to account for the size of our horn antenna. Just as a side note on how this works, RF energy in the form of electromagnetic waves travelling towards the antenna in a plane wavefront will be reflected by the reflector and remain in phase at the focal point. That's where our horn is positioned. In this way, the whole signal remains in phase and there is no cancellation. This means that the maximum signal is maintained. Conversely, signals radiated from the focal point, which is where our horn is positioned, will be reflected by the parabolic reflector and form a parallel wavefront, which is in phase, travelling outwards from the antenna. There are 3 different approaches we could take to solving this simulation. We could do a full 3D time domain solver, which would require 3D discretization of the 3D space between the sender and reflector, and would result in billions of unknowns. We could do frequency domain analysis of the full structure using the integral equation solver, which would have a moderate runtime for the simulation, but only the surfaces will be discretized, and analysis is more challenging for a very complex feeder. Or we could use the proposed workflow, which is the hybrid solver, which is 2 simulation projects, one for the horn antenna and one for the reflector, sequentially simulated and coupled via a hybrid solver. The horn antenna would be a source and will be simulated using the T solver, and the reflector, which is our platform, would be using the I solver. The prediction of electromagnetic fields scattered in a complex and electrically large environment is usually a difficult task due to the high aspect ratio between the smallest details and the overall calculation domain size. Even though a variety of numerical methods have been developed over the past decades, these simulations typically cannot be done by a single numerical method, also known as brute forcing it. The capabilities of taking advantage of more than one numerical method at the same time to get the desired results is crucial and commonly referred to as hybrid simulation. The separation of complex problems into multiple parts, with the link between them being defined by equivalent near or far field sources, can dramatically speed up the installed antenna performance and the antenna co-site analysis, and in many cases makes possible what is otherwise not feasible. Hybrid simulation can be easily set up by the hybrid solver task that relies on the system assembly and modeling infrastructure. 2 similar workflows are available. The unidirectional hybrid solver task has the sources being calculated first. The coupling data is loaded into the platform and used as excitation for the final simulation. In CST Studio Suite, all solvers support this task, but unfortunately no backscattering of the platform toward the source is taken into account. For the bidirectional hybrid solver task, the source and platform exchange coupling data iteratively until satisfying a convergence criterion. At the moment, only T solver and I solver are currently supported, but the backscattering of the platform toward the source is taken into account in this situation. For this analysis, we are using the T solver and I solver, so we will choose a fully coupled approach in order to consider the horn blockage effect on the overall far field performance of the reflector antenna. So let's select bidirectional. We then select reflector 1 and go to 3D model, create simulation project, we'll call this reflector. Make sure we're using the integral equation and select OK. We then select horn, 3D model again, create simulation, we'll call this horn, and then make sure we're using the transient solver. Select OK again. We can then close project or close simulation project mode, and all the simulation projects will be created together in a final step. We specify the near field coupling frequencies as 10 to 10 gigs. We only want one frequency sample. And if we press OK, if we then go to our task parameter list, I have mine set here, but it might be in a different location for yours. If you go down to global iterative solver and select the maximum number of iterations as 3, and then select update. Each simulation project is automatically created and is accessible as a standard 3D project. Each of these has one pair of field sources, one field source monitor to write the field data, and one field source to print the data loaded from the other domain. Now our simulation has finished running and all the calculations have been made, we can check our far field results. So if we go to our reflector far field, and look at our 1D results, we can see we have a fairly focused antenna where the side lobes are minus 21.5 dB and the angular width is 6.6 degrees, where our main lobe magnitude is just short of 30 dB. With system and assembly modelling, we can perform looped parameter sweeps and optimizations. This means we can loop a parameter such as the horn radius that we used in episode 1, and we can modify this to sweep whilst also producing our far field results from the hybrid solver with our reflector antenna. If we go to our assembly tab and define a new parameter, we'll call this horn underscore radius. We set this to 1. Then we select the horn block and find our previous horn radius, which we defined in the previous video as aperture O. When we set this to horn radius, we can see it's possible to autocomplete this. They now become combined, so if we were to change our horn radius in here, the value also changes in our aperture O, which is from the first block. And you see the aperture gets bigger. Let's change this back to 1 for now. If we then go to tasks, select new task, and then a parameter sweep and press OK, we can then double click on the sweep, select a new sequence with a new parameter with our horn radius between 1 and 1.5, and we'll look at 3 samples. We then close this. We now go to HS1, left click and drag this into sweep 1. We can then also go to sweep 1, right click it and select new task, select post-processing, far field and antenna properties, and far field result. Select directivity, constant, phi equals 0. Go to all settings. For the reflector, browse results for the far field horn. Look for 1D Cartesian with a step size of 1 and directivity changed to realized gain for the plot mode, and select OK. Close this, and now we can update again and we'll be able to compare the 3 different horn radius sizes and how this affects the overall gain of the antenna. Now that our results are finished, we can see that our task took 29 minutes on a CPU only driven PC, which if you're using hardware acceleration may be improved from anywhere from 4 to 6 times faster. But anyway, going back to our results, if we go to our post-processing and our 1D results, we can superimpose all 3 of our horn radiuses, which are 1, 1.25 and 1.5 on top of each other. And we can see they all have a very similar gain profile. But we also know that the maximum realized gain for the whole system is not directly proportional to the horn aperture radius, and this is because of the increased blockage effect of the horn, which is screening the radiation from the reflector. So whilst the initial gain may be improved coming out of the horn, the blockage factor is definitely playing a part. Now this brings us to the end of this session. And I would like to thank you all for watching, and if you have any questions, by all means, contact us at sales@castlemicrowave.com, or please feel free to leave comments in the comments box below. And in fact, if anyone watching also would like to ask questions or help each other out, that would be great. As the microwave community, we all work as a team together on this, and I'll be down there hopefully answering some of your own questions myself. If you like this video and would like to see more content from us, please feel free to leave suggestions, and like the video, subscribe to be ready to see when more are available, and hitting the bell icon will allow you to receive notifications. I've been Josh. Thank you very much.